Inside modern hardware, data moves at staggering speeds. Trillions of operations cycle through silicon pathways every second. But raw speed hits physical walls, bringing that momentum to a dead stop. In distributed computing clusters, processors have disjoint address spaces. They communicate by sending messages over a network bus. When thousands of nodes try to share data simultaneously, that bus chokes under the communication overhead. Inside a single processor core, very long instruction word pipelines try to execute multiple operations per clock cycle. But if one instruction depends on the result of another, the pipeline stalls, wasting valuable clock cycles on empty dependencies. Then there are SMD vector registers, designed to process contiguous blocks of memory all at once. If that data isn't perfectly aligned to the strict physical boundaries of the hardware, the entire operation faults. Finally, there is memory latency. A CPU cache sits completely idle, starving for data to arrive from main memory, because the physical distance simply takes too long to traverse. To a systems programmer, network routing, instruction scheduling, memory alignment, and cache latency each demands its own specialized toolset and optimization strategy. But an optimizing compiler does not see the physical wires. It does not see the network, the registers, or the silicon cache. To the compiler, these four separate physical bottlenecks are the exact same mathematical problem. They are all resolved by a single framework, the Affine Access Function. This equation translates the execution of loops and array references into a multidimensional geometric space. An array access is considered affine if its index is a linear combination of the surrounding loop variables. It maps a specific point in an n-dimensional iteration space directly to a specific memory location in the data space. This theory was originally developed to parallelize code for shared memory symmetric multiprocessors. Today, it acts as a universal engine, calculating the exact spatial and temporal coordinates needed to optimize distributed clusters, instruction pipelines, vector units, and prefetch controllers alike. Consider a message-passing distributed cluster or a non-uniform memory access architecture. These machines connect independent processors, each with its own local memory, across a larger network. If every processor attempts to share all of its data constantly, the sheer volume of traffic overwhelms the interconnect bus. The communication cost quickly exceeds the benefit of computing in parallel. The compiler must prevent this traffic jam. Its goal is to carve out large, mathematically independent blocks of computation and assign them to specific processor IDs, minimizing the need for network communication. It does this by using affine partitions. The compiler takes the entire multidimensional iteration space of a program and mathematically slices it, mapping distinct iterations to separate physical processors. To figure out which data each partition needs, the compiler uses a technique called projection. It takes the mathematical loop limits and projects them directly onto the array access function. This calculation pinpoints the isolated subsection of an array that a single processor will touch. Every processor receives only the bounds of the data it explicitly requires. Where those data requirements overlap between processors, the compiler automatically generates explicit send and receive instructions at the exact boundaries of the partitions. Unnecessary network traffic is now completely eliminated. That alone solves the macro-scale routing problem, but the exact same math applies when we zoom in to the microscopic scale of a single execution core. Modern execution cores, like the Intel Itanium 2, utilize very long instruction word and superscalar architectures. These processors issue multiple operations simultaneously within a single clock cycle. Their performance is strictly limited by data-dependent cycles. If instruction B requires the output of instruction A, B must wait. This delay creates an execution bubble, an empty gap where the hardware does absolutely nothing. To eliminate these bubbles, the compiler applies loop permutation, swapping the axes of the iteration space. This pushes independent iterations into the innermost loop, shattering precedent cycles. The compiler continuously feeds the VLIW pipeline, leaving no empty cycles. Even without dependencies, a pipeline can stall if resource usage is unbalanced. That is where another affine primitive comes in, loop fusion. If one loop heavily taxes the arithmetic logic unit, and another loop only performs memory loads, the compiler fuses their mathematical domains together. Now, the processor uses its computational units and its memory units simultaneously, maximizing hardware utilization. Routing data packets across 1,000 separate nodes, or scheduling instructions in a nanosecond pipeline, two vastly different physical realities, governed entirely by reshaping the geometry of the iteration space. This geometric approach also solves the physical constraints of data alignment. In early supercomputers, vector instructions fetched data serially, overlapping computations on massive specialized hardware. Today, that architecture has been miniaturized. High-performance microprocessors use specialized SMD registers to apply those same vector concepts directly at the chip level. SMD stands for Single Instruction, Multiple Data. It allows a processor to issue one instruction and simultaneously apply it to a wide, contiguous swath of memory locations. But this hardware is physically rigid. It requires perfect alignment in memory. If misaligned, the instruction simply fails. The compiler enforces this alignment using strip mining, segmenting the iteration space into blocks that match the SMD register's exact width. For unaligned edge elements, it creates a specialized prologue and epilogue loop, allowing the main loop to execute safely on perfectly aligned blocks. With the vectors aligned and the pipeline fed, the processor faces its final and most severe physical bottleneck, memory latency. No data locality optimization can eliminate all memory accesses. When a processor requests data not in its local cache, it suffers a cache miss. The processor halts completely, wasting hundreds of cycles waiting for data from main memory. Processors have prefetch instructions to load data in advance, but guessing is a very dangerous game. Fetching data too early displaces critical information already residing in the cache, causing even more delays. To hide this latency, the compiler relies on affine reuse analysis. It acts as a mathematical crystal ball. By analyzing the null space of the access matrix, the compiler maps the exact temporal and spatial coordinates of the data. It calculates the precise iteration where a cache miss is guaranteed to occur. Knowing the future, the compiler uses software pipelining to schedule prefetching with perfect timing. While executing iteration I, it dispatches a request for iteration I+6. The fetched data drops into the cache exactly when requested, completely hiding the latency. By utilizing affine transformations, the compiler manipulates space for SMD alignment and orchestrates time for cache prefetching, ensuring the hardware is constantly fed. We've looked at networked server nodes, at VLIW pipelines, wide SMD registers, and physical cache latency. Yet the optimizing compiler is entirely blind to these physical constructs. It knows nothing of wires, buses, or silicon structures. Instead, it models the execution of a program as a multidimensional polyhedron. Every loop, every variable, and every memory access exists as a coordinate within that mathematical iteration space. Manipulating the boundaries of that polyhedron using linear, affine transformations is the true engine of software optimization. Whether the engineering objective is improving spatial locality for memory, ensuring temporal locality for cache reuse, or extracting raw parallelism for a supercomputer, the underlying math remains identical. True execution speed requires hardware to move data, but achieving that speed is a geometry problem.